this week. All of my classes this semester, all of the tests are on like a 3-week cycle. Like seriously, all of them. So I'll have like one test a week, and then
And then
3
you're
week, 6 texts a week. Tests. Yeah, I know. Whatever. I don't know if anyone ever listens to these. So he just wants to do that. Anyway, whatever. Okay, here we go. Oh, okay. Oh, jeez. Yeah, I got finish mine. Do you have to take 377? Bio 377. It's the one that goes with this. It's techniques in biochemistry. No. It's actually a really cool class, but it's really hard too. It's a lot of work.
I just have to do bioforce and follow up chemistry.
Is 475 self-evolution? Evolutionary science. Yeah. Okay. Anyway. So transcription in E. coli is divided into 3 stages: initiation, elongation, and termination. I said actually goes right along with what we're doing in class because we're doing cloning. So you clone by inserting DNA into E. coli. Anyway, what DNA sequences are involved in initiation?
Initiation? What's termination one? I can see why I accidentally forgot the original. But I got the promoter. One of the termination sequences involved in initiation.
Yeah, I think that might be So I think it's regulatory because they were listed again down here.
Yeah.
So that's what I figured.
Oops, I forgot to go back and correct that. Because with proteins, like, I knew the sigma factor. And I forgot to add that early.
Yeah. Oh wait, did you forget the sigma factor or the DNA polymerase? RNA polymerase, sorry.
Yeah, I got the polymerase, but I forgot to add in the sigma factor. Like, I knew it was protein, but I don't know why I didn't click to write it on here. Oh, wait, no, I did.
Yeah, you got it.
I was looking at C.
Oh, okay, we can go to C. Well, it's going to be. So you have your RNA polymerase 4 enzyme as an elongation. And then DNA sequences are involved in termination of E. coli as the terminator sequence. There we go. Yeah, that's what I thought. I was like, I think it just goes down with termination. But
Oh my god! My thumb is really starting.
did you like get some jalapeno or something on it?
Well, I think it got under the meal just a little.
Yeah, I always get that sometimes. Normally I have no issues with garlic, but occasionally, oh yeah, it doesn't help. But if I make salsa, I have to be so careful with the jalapenos. So we'll get under the burns. Anyway, sorry, back to our thing. This video is so like crazy already. Okay, what proteins are involved in termination of E. coli? You have the Rho protein and the. Are we good with proteins?
Yeah. Okay. My tongue now down. That's my thumb on it. Now my tongue is bleeding.
Coli produces a family of proteins called sigma factors. What is the function of a sigma factor? Sigma factor associates with RNA polymerase coenzyme to form the RNA polymerase coenzyme. Yeah, so it just talks about how signal factors associate with the RNA polymerase to make the holoenzyme, and they guide the RNA polymerase.
That is
So the RNA polymerase where to go. And that's called that you have a housekeeping signal factor. I didn't get this one. But one third of this makes sense. So housekeeping refers to all cellular functions in E. coli that are required for life. Therefore, the housekeeping signal factor functions to guide the RNA polymerase coenzyme to control of all genes essential for life. In E. coli, this ensures that these essential genes are continually transcribed.
Yeah, so I put transcription also.
Yeah, I think that the housekeeping, it's like it's that they're essential, and because of that, they kind of have to. I think it's like that they're continually transcribed. Does that make sense? Yeah. So like it's housekeeping because it's like constant. You know, it's like constant. Oops. Oh.
I prefer green salsa. Anyways.
All our signal factors important for the general starvation, nitrogen starvation, and excessive heat signal factor.
So these all deal with like the transcription.
Yeah. Yep. Basically, you just have to work on like what's your main factors. Signal factor is a good example of a transcription factor. Provide 5 other examples. In E. coli, terminates transcription using either the P-dependent or
P-dependent requires the rel protein in the
yeah, binding to the RET sequence.
And the P-independent doesn't require the rel protein nor the RET, but does require the amino acid.
Yeah, it's spontaneous dissociation. Yeah. No weak hydrogen bonds in the dependent. So how are these two mechanisms similar?
They both require stimulant.
The stimulant structure. And that stalls the RNA polymerase coenzyme.
Yeah. Flows.
Suppose you were studying how P-dependent transcription information in the lab. Specific changes you can make to the DNA or mRNA that would inhibit transcriptional termination.
Yeah, so I put change or remove the RET. Mutations and
yeah, I talked about like the stem loops, right? So so you can't make those fragments.
I also said change or remove the DNA sequence formation.
Yeah, exactly. So it's basically like the RET sequence or the stem loop. Yeah. Cool. Suppose you were studying P-independent transcriptional termination line. Suppose to is being referred to P-independent transcriptional termination process. DNA or mRNA to inhibit transcriptional termination. So I took stem loops or another one. Yeah. Like there's still like both of them need it.
Change or I put change or like mutation in the adenine region. So that it like because that's the region that causes the DNA region that causes this.
Yeah, the hydrogens dissociating the weak hydrogens.
Yeah, and so I put a
yeah, to not dissociate. Yeah, it's the spontaneous dissociation. Yeah.
core promoter, box, and
Mm-hmm.
then the polymerase T and description factors, which include the knockout button. At least that's what it said
Mm-hmm.
on the FDI DBFD page.
Yeah, so different transcription factors. There's a lot of them.
And then for C, core promoter elements, cat box, GC box, and whatnot.
Mm-hmm.
And the regulatory elements.
Alright. What proteins are involved in regulated transcription factors?
Regulatory transcription factors transit and polymerase to GTS. No. This question concerns the discussed in this similar which are the ones so
Now, suppose a pre-mRNA is produced by transcription. Which RNA modification occurs first? Which RNA modification occurs second? And is the final RNA modification?
well,
Yeah, so it's like with the caps and the splicing. Yeah.
Intron splicing. So happening. So it'll be
Sure. Yeah. Oh, okay. So modification. First, you have RNA capping.
intelligent generation evidence
Yeah. Alright. Should we check your answer?
Yeah.
RNA capping. Yeah, polynylation splicing. So first you have an end cap and polynylation. Then you splice out the introns. Okay, B. Ah. So I'm trying. My word is being so finicky lately, and I think it's because I still have this giant report up from another class. It's like 12 pages, but I need to keep it up because I'm still working on it. Okay.
Ribosomes play an important role in RNA modification. What is a ribosome? And which RNA process is involved? So a ribosome is something that leads the art.
And it attaches to the RNA and all
Yeah.
this red.
And so yeah,
No, so that does not involve in modification though. You're looking at the instructor's notes.
yeah. Which reason is this?
I don't know. I think we're supposed to do it together. Discuss and solve one put together. I don't think so. I guess putting in the video is probably okay. So it doesn't say anything here. So I don't know how they affect modification. Ribozymes. Sorry, ribozymes. That's why we're so confused. It's ribozymes. Gosh.
So
This is a stupid question.
splicing.
Yeah,
Splicing.
ribozymes, enzymes always are. RNA splicing.
Yeah.
Yeah.
I was looking for ribosome and not ribozyme.
Yeah, me too. I was like, what do you mean they're involved in this?
Yeah.
A ribosome is a catalytic RNA molecule. Intron splicing involves the use of ribozymes. Nailed it.
Yeah.
After looking for a long time for the wrong thing. Okay, what is the function of each of the following molecules in RNA modification? Probably with my ears because it's missing. This is online here.
Yeah. What is the function of each of the following molecules? Okay. SNRN. So small nuclear ribonucleic.
I like that people call these SNRPs. Like, I like that people do that. It's different. Okay, sorry. They form a spliceosome. Spliceosome, sorry.
Yeah.
Oh,
They're second.
And then they, which helps in the splicing of the mRNA.
Yeah. Two small nuclear RNA splices on the catalyte. So they help catalyze.
It also helps to recognize recognizing the sequences of critical splicing signals of the five patterns. SNRF until the segments of the splicing complex. Got it. Which contain ribozymes that remove introns from most eukaryotic nucleotides. SNRFs contain proteins and snRNAs.
Want to see the nucleus. guanosine nucleoside. Binding of so the guanosine is a cofactor for the reaction that takes place at intron binding.
Can you see? Where are you looking? Okay. Binding of the free guanosine nucleosides to binding site of intron. In this reaction, the guanosine serves as a cofactor for the reaction. Formation of a break conjunction in the first exon of the intron, the guanosine is attached to the 5' end of the. So, no, I think that's right. I think it serves as a cofactor.
Yeah. But it doesn't seem anything else more about the nucleoside.
Cofactor for group 1 intron twice.
What is it? So, fluid and polyhydrogenation
Specificity.
Yes.
Specificity, it's a hard word. I was like looking at that and thinking really hard about where the emphasis goes and like specificity. Oh my gosh. Cleavage and polyadenylation specificity factor. That is a mouthful.
Which is why
It's involved in the cleavage of the 3' signal region for mainly cells. Free messenger of RNA. Yay! 3' polyadenylation. Oh, okay, this is necessary. CPSF recognizes the polyadenylation signal sequence in the pre-mRNA.
Yeah, that's what it is.
And cleaves the pre-mRNA to 10 to 35 nucleotides downstream of the polyadenylation signal sequence. Oh no. Oh no. No, spoilers. Don't mean it. Polyapor. So then I just make the polyapor. Like, I think polyapomers literally just has the poly in the tail.
Yeah,
Like, I think it just does polydenylation. I'm pretty sure it's fine. You check that?
yeah.
Hey! Polypolymerase is involved in 3' polyadenylation. Binds to the 3' end of the pre-mRNA donated by a sequencer and has 250 A bases to form a polydate. Okay. Guanyltransferase.
Guanyltransferase recognizes the
Hydrolyzes.
GTP to produce GMP and attaches 5 carbon TPG to the hydrocarbon of the nucleotide. Note that this is an unusual hydrocarbon. priming. That's 5 priming and 5 priming.
Yeah, I don't understand like why it hurts.
And hydrolyzes.
Oh, it's the cap.
Oh.
Yeah, that's the 5 prime cap. When it touches the 5 prime
Okay.
end to the 5 prime end,
Yeah.
that's the cap on the 5 prime end. Okay,
Okay.
I totally get it. Sorry, that was like. That's probably kind of a dumb thing that I didn't understand it the way she wrote it, but. The transfer guanosine monophosphate, known as a GMP, usually from GTP to another molecule is pyrophosphate. Many eukaryotic guanylyl transferases are capping enzymes that catalyze the formation of the 5 prime cap in the co-transcription modification of messenger RNA. Yep. 5 prime to 5 prime triphosphate linkage instead of the 3 prime to 5 prime linkage. Guanylyl transferase is involved in 5 prime end capping. Guanylyl transferase cleaves are GTP, produce GMP, and PP. When the GMP is then covalently linked by guanylyl transferase to 5 prime end. Got it. Alright, introns are often identified by examining the results of hybridization experiments in the electron microscope. The gene contains 2 introns. Draw an image that represents the result of the hybridization experiment when the template DNA strand is hybridized in the mature mRNA followed by hybridization of the coding. So it just wants us to like draw the removal of the introns.
Yep.
Template DNA for mature mRNA.
Yep.
Hybridization.
All of that.
So you want to draw the hybridization of DNA into mature mRNA.
Yeah.
To mature mRNA. Okay. with yourself. Mhm.
Well, how lucky I was this
I'm not sure. Let's look in the instructor's notes.
I will pull up the PowerPoint to see if that helps.
Good, yeah.
PowerPoint is a lot more.
I think like with hybridization, as far as I can understand it, they're just gonna draw like DNA and the mRNA, but they're gonna be complementary sequences. So once you separate them, once you denature them, then they can come back together as I see. Yeah. Uh-huh. Yeah, so basically we would just assemble the two intron nodes because the mRNA has the introns spliced out, and then there's still introns in the. Yeah, I know how to do it. It's like, one. Let's just do one. Wow. If we force switch it, you know? Not that that sounded really mean. I enjoy working with you. I just mean like that they are like telling us that we have to do one part together.
Yeah.
Okay, so I think you start out with your.
So we can do.
You have to have two intron solid
Yeah.
space for those. And yes, we do.
Oh, I was looking at
DNA. This is
Oh,
DNA.
that is the DNA. There's
Yeah, look, so here's the DNA. And here are its introns. And then. Do you want to use my one?
Oh, yes.
So. Give me like a lighter yellow and a lighter green. So then we can show you what the sequences are like. Ordered. And like a light yellow. Yeah, like the same thing yellow. From this, we're gonna make ourselves some mRNA. This way it shows that the introns are not same. Right? So that's our.
What it looks like, yeah.
Here. Our regular areas of okay, and so then you're going to have this is going to be processed. You're going to have a 5' cap poly tail, and you're going to remove the introns, right?
Yeah.
So that leaves you with you could actually want to add the caps.
Yeah, we can have the caps.
Just give me like a crochet or something.
And then
And then that's going to rehybridize to the original strand of DNA.
I think so.
Yeah, so you have your original strand with introns still on it. And then you're going to put together. Hybridized. And your final product is going to be your mRNA attached, or you're going to have sequences of DNA with the introns with this. Yeah.
That looks great. And then oh, that would be the two both strands would be okay. Yeah.
Yeah.
That's good. That looks nice.
Okay, let's go ahead. Let's check the questions here. Anything. For the Jenkins 2 introns. Draw an image that represents the result of hybridization experiment. The template DNA strand is hybridized to the mature mRNA, followed by hybridization with the coding DNA strand. Oh yeah, you're right. We have to have the coding DNA strand too. Like that.
Okay, that's nice.
Okay. That's just a bit. I don't want to do that. So
Oh,
here we have our what?
and then you, yeah, the orange
Oh.
and the top one.
Go to the all right, we'll label it.
Yeah.
This is the template strand, right?
Yeah.
The coding strand has the heart roots.
I believe so.
Yeah. Template. True. this is our complete strand. This is our floating strand on top. These are our color groups. Yep. I think that's good.
Yeah.
So here we start out with synthesizing our mRNA from our original sequence with our coding and our and then synthesize the mRNA, process the mRNA, so we added a tail and a cap, and remove the introns, and then it hybridizes back to the original DNA, creating this, where it has the loops, these little inside loops, where the introns are, and then the coding strand templates over the top of that. And so you have not only the intron loops, but also the other loops. Haha!
We only did one drawing because we.
It always seems like one of us decides to be more detailed than the other, so if we do it together, then one of us is reading.
Yeah.
Alright. I think we're good. We're good, yeah?
Yeah.